Welcome. This lesson is the first in our unit on recursion, so let's get started. We've got three learning goals for today. The first is that you can explain the concept of recursion as it relates to computer science, that you can identify the base case and recursive call in a recursive method, and finally, that you can write recursive methods in Java and use them to solve problems. Before we dive into any code, we really need to get our head wrapped around the concept of recursion. And broadly speaking, recursion is when we define a problem in terms of itself. You can see this in the function on the right. On the left side, we say f of x, and we're used to that from math class. But what maybe we're not used to is also seeing f of x show up on the right. The function uses itself in the definition. So how does this play out? Well, let's look at an example where we try to compute f of 7. In order to find f of 7, we know that from math class, we need to take our 7 and we need to substitute it in for x in our function. And we've got two choices. If our x is greater than 2, we'll use the top expression, and otherwise we'll use the bottom expression. So since 7 is greater than 2, we'll substitute our 7 right here and end up with f of 7 minus 2 plus 2. Now 7 minus 2 can be simplified to 5, so f of 7 equals f of 5 plus 2. So I've done something, but I'm not at an answer yet, and that's because our answer depends on what f of 5 is, and we don't know. So we'll treat f of 5 as a new problem to be figured out. So f of 5. 5 is still bigger than 2, so we'll use the top equation and substitute our 5 right here. And we'll end up with f of 5 minus 2 plus 2. And just like before, 5 minus 2 can be simplified to 3. So we have f of 3 plus 2, but again, we don't know what f of 3 is, so we'll treat it as a new problem. 3 is still bigger than 2, so we'll substitute our 3 right here and end up with f of 3 minus 2 plus 2, which is the same as f of 1 plus 2. So it seems like we have the same problem as before, and maybe we're going to just keep going forever, but actually this is going to be our last step. We'll treat f of 1 as a new problem, and 1 is no longer greater than 2, so we move to using the bottom expression. So x plus 2 would be 1 plus 2, which is 3, and we've arrived at a point where the recursion has stopped. And we have an answer, and now we can use that answer to get what we really wanted. So remember that f of 3 depended on knowing what f of 1 is, and now we know. So we can substitute our 3 in, and 3 plus 2 is 5. So f of 3 is 5. And I can use that then to get f of 5, because f of 5 wanted to know what f of 3 is. 5 plus 2 is 7. And finally, in my last step, I can substitute. I now know that f of 5 is 7, and 7 plus 2 is 9, making my final result, f of 7, what I wanted to know in the first place, equals 9. Now that we've done one of these recursive functions together, I'd like you to try one on your own. For this case, I'd like you to do f of 7, 4. So notice that there's an x and a y to substitute in for, and we've got the three expressions. This one actually doesn't have very many steps. Just make sure you notice that in the third expression, the y and x change places, because if you miss that, it'll be really easy to get it wrong. Pause the video, and on the next slide, I'll show you the solution and the steps I took to get there. F of 7, 4 should equal negative 3. You can see that I took 3 steps to get there, eventually landing at negative 5. And then I took the negative 5 and substituted back up here. 2 minus negative 5 is 7. And finally, 4 minus 7 is negative 3. So if you made a mistake, I would encourage you to pause the video here and just kind of walk through these steps and correct your work before you move on. Let's try one more. In this one, we want to find f of 13 given the function shown below. Pause the video, grab a sheet of paper, work it out, and when you're ready, on the next slide, we'll talk about the answer. After doing all the steps, f of 13 should equal 31. You can see my steps on the left, and if you didn't get 31, I would encourage you to pause the video, walk through those, and figure out where you made a mistake. I eventually landed on 1 and 0 for f of 6 and f of 5, and then substituted them back to get the final answer. As we did the last few problems, you may have noticed that they all sort of had the same pattern. Recursive functions in general always have two features. First is they all have a recursive call where the function is defined in terms of itself, and they also have an expression or an equation that stops the recursion. This is called the base case, and this has to exist because if it doesn't, the recursion will just go on and on forever and we would never reach a stopping point. Now that we've seen how recursion works in the math world, let's talk about how that translates to Java. So in the math, we have a function called f with a parameter x, and in the Java code below, we have a method f with a parameter x. In the math, if x is more than 0, the result is 3 times f of x minus 1, and the same is true of the Java code. If x is greater than 0, we return 3 times f of x minus 1. In the math, otherwise, we return 2, and in the Java code, otherwise, we return 2. So then let's say in our Java code, we call our method f with parameter 4. What does Java actually do? Well, just like the math, it substitutes the x and it realizes that 4 is greater than 0, so it will return 3 times f of 3. But Java can't return from the method yet because f of 3 is unknown. So what happens is Java calls the method again. Basically, our method calls itself, but this time with the parameter 3. And so now I actually have two methods hanging out. F of 4 is waiting to return, and it's waiting to see what f of 3 gives it. So f of 3, Java receives the 3 parameter and realizes it's greater than 0, so Java will return 3 times f of 2, except it has to wait because Java doesn't know what f of 2 is, so the method calls itself yet again. So for f of 2, x is 2, and Java realizes that that's still greater than 0, so Java is going to return 3 times f of 1. But Java doesn't know what f of 1 is, so the method calls itself yet again. When we get to f of 1, Java still sees that it's greater than 0, so it will return 3 times f of 0, and the method calls itself again. But at this point, we've hit our base case, because 0 is not greater than 0, so it returns a 2. So the 2 gets returned, and finally f of 1 can finish because it was waiting on f of 0. 3 times 2 is 6, and it returns. And now f of 2, who was waiting, it was waiting to return 3 times f of 1, can do that because it now knows f of 1 is 6. 3 times 6 is 18, 3 times 18 is 54, 3 times 54 is 162, and finally, our original method f of 4 can resolve. It was waiting that whole time for f of 3, and once it got it, it was able to return the answer. When we're making recursive methods in Java or any programming language, the base case is so important because it's what stops the recursion. So in the code below, I took the base case out, so all it does is return the recursive call, and you can see what happens. F of 4 calls f of 3, calls f of 2, calls f of 1, calls f of 0, calls f of -1, calls f of -2, and it just goes on forever. And because this method is calling itself so many times, the computer actually runs out of available memory and throws what's called a stack overflow exception. If you've ever visited the website for a programming question, Stack Overflow, this is where it gets its name. And it's something that's easy to do and something that we have to be careful about. Our base case has to be on point to prevent this from happening. So in this lesson, we looked at recursive solutions to problems, and we understand now that that means we define the problem in terms of itself. And in Java, that means that we have a method that's calling itself. And there's certain problems that we'll encounter where recursive solutions are incredibly helpful. Of course, not every problem requires a recursive solution, and problems that are not solved recursively are solved iteratively. This is how we've always solved problems before, but we never put a label on it. Basically, iterative solutions define a problem in a step-by-step way. The code on the right produces the exact same output as the recursive function on the previous slide. However, the iterative approach uses a loop to repetitively multiply by 3, where the recursive solution, the function called itself over and over to get that repetition. Now, any problem that can be solved recursively can also be solved iteratively. However, there are some problems where the recursive solution is much simpler to implement. For our understanding check today, we'll start with an iterative method called sum. And what this method does is it uses a loop to add up the first n integers. So if I was to say call sum 3, it would end up returning a 6 because the loop would add together the numbers 1, 2, and 3 to get the final solution. So what I'd like you to do is write this as a recursive method. And what you need to do that is you need to think about how could this summing problem be defined in terms of itself, and what would be the base case to stop that recursion. Think about those two things, pause the video, and when you're ready, we'll see the solution on the next slide. First, we identify our recursive relationship. The sum of the first three numbers is 3 plus the sum of the first two numbers. And the sum of the first two numbers is 2 plus the sum of the first number. And of course, the sum of the first number is just 1. This is our base case. So in general, the sum of the first n numbers is n plus the sum of the first n minus 1 numbers. And here we can see that in Java code. If n equals 1, return 1. Otherwise, return n plus the sum of the first n minus 1 numbers. Now that you've watched this lesson, you should be able to explain the concept of recursion as it relates to computer science, identify the base case and recursive call in a recursive method, and be able to write recursive methods and use them to solve problems.